Okay, we're going to do a synchronous counter design today. So we're going to design a synchronous counter. And we're going to, first we're going to do that from a state diagram. We're going to use D flip-flops. And then we're going to create a circuit in with the Xilinx ISE. And then we'll simulate it. Okay, so I've got a state diagram. I want the counter to count in this order. And I'm going to use D flip-flops. And remember, for a D flip-flop, if I have a input if I want my cue to progress from an initial state from 0 to a 1, all I simply need to do is have a 1 at the input D. So the D input just needs to reflect what the final state is. So in order to get a handle on this, I simply make a table and I count up in the normal fashion with my initial state. So this would be my initial Q state, three flip-flops. So if I start at 0, 1, 2, and so on, count up to 7. And then my final state, after the clock pulse comes through. So if I start at 0, my next state is 1, 1, 0, 0. Okay, now if I'm in the 1, 0, 0 state, down here, my next state is the 1, 0, 1 state. And if I'm in the 1, 0, 1 state, my next state is 0, 1, 0. Go up and find 0, 1, 0 here. And then the next state is 1, 1, 0. 1, 1, 0 goes back to 0. And then all these other states that are not used or don't care. Okay, and because this is the final state, the D initial input just has to reflect the final state like we had in our excitation table over here. So these rows just translate over into the D. Okay, so the next thing I'm going to do is create a logic expression for D2 based on the initial state of Q2, Q1, Q0. So I'm going to put these values into a Carnot map with these as the arguments. So D2, I map into the Carnot map, and because I count up in the normal fashion, I simply can record these values in a pattern as I fill the table. So 1x, 1x goes into the table 1x, 1x, the way we fill up a Carnot map. So I do that for D2. I make my groupings. Don't care, R can only help. So I have two groups here. I have Q2 naught, Q1 naught, and Q0 naught. Okay, then I do the same thing for D1 and D0, logic expressions for those. Okay, now that I have my state diagram and my flip-flops designed, more or less, I'm going to now implement it in an ISE design. So I'm going to open Xilinx ISE. I have a project that already exists, although I could create a new project, but I'll start with this existing project and there's no sources in it. So I'm going to add a source and it's going to be a schematic file. All right, so my design, now I'm in implementation mode and I've got a new design added to my project. And now I'm going to add some components to it. I'm going to need 3 flip-flops. And rather than create 3, I'm going to create what I need and copy and paste it. I also need an inverter. Because I need the Q0 output, which this feature doesn't have. And let's zoom in a little bit so I can see it. I'm going to draw nets. And I need an output port. Okay, I'm going to need 3 of these. I forgot to put a net here. So you need to add these little nets so you can use them later. Select everything. Control C, Control V. All right, 3 flip-flops. Now I'm going to name these. So I'm going to right-click on this. I'll call this D0. Q0. Q0 no. And I don't know why the name appears, sometimes it doesn't. If you double click on it though, you can see that it was renamed. And this is going to be my clock. And I'm just going to call it KLK. I'm going to call this one KLK. And it's going to ask me, do I want to join them? Yes. So now these are effectively connected. D1. Q1. D2. D2 now. Okay, so I've got my 3 flip-flops. Let's just see how this compiles at the moment. I probably have some errors because I'm not connected to some things. It's telling me that the clock is not connected, nor is D0, D1. So I'm going to create another input port for these. Let's see, how do I do that? Create a net first. Okay, now I'm going to connect an input to this. That's my clock. Okay, so all 3 of these clocks are connected to the same input. Now I need to realize the circuit that we designed for each of the Ds. So for instance, D2 is Q2 naught, Q1, and Q0 naught. So let's go make that circuit down here by D2. All right. So that was one AND, two input AND gate, one OR gate, okay, so this was Q1 naught, and this was Q0 naught. And this was Q2 naught. And this one will feed into D2. Just check it. So this is connected to that even though it doesn't say it. Okay, so is that exactly what I had? Q2 naught, Q1, and Q0 naught. Okay, that's what it is. Okay, now I'm going to do that same thing for these two, but I'll spare you the details. All right, so we've got our full design. I've added these two for D1 and this guy for D0, and those reflect these logic expressions here. So now I'm going to simulate the design. So let's first compile it. Let's make sure that it compiles. Still in implementation mode. Okay, so now I'm ready to simulate. I don't have to create the board design because I'm not going out to hardware. I'm just going to simulate. So I'm going to click Simulate, select my project here. If if I select the project, it won't work. I have to select the actual design. And then I'm going to use ISIM simulation. So double click on that. Okay, note that I have one input, the clock, and three outputs for Q0, Q1, and Q2. So in my simulator, I'm going to put in, force this to be I'm going to force clock, so I'm going to right click on the clock. So it's giving me all the nodes in here, but I only need these four here, the input and then the three outputs. So I think I can hide these. And, well, I'll just leave it like that. So clock, right click, force clock, start it as 0, go to a 1, let's do it every 100 nanoseconds. And then run the simulator. I'm going to try to relaunch here, something. Try it again. Okay, let's see if that took. Sometimes the time scale here is such that you can't see your actual clock pulses. So here you can see the clock pulses. Let's expand it a little bit. And remember that we started at 0. So I have a little guide here, and I can see my value of my Qs over here. So 3, I'm starting at 0, 0, 0 for Q0, Q1, and Q2. And then as I slide it down here, I go to 1, 0, 0. And the next one was 1, 0, 1. And the next one was 0, 1, 0. So let's see if that's following what we initially wanted. 0, 0, 0, 1, 0, 0, 101, 0, 1, 0. So the next one should be a 1, 1, 0. And it's a 1, 1, 0. And then we go back to all zeros. And it repeats. So we showed that our counter, we designed the counter using this method, created logic expressions for each of the D inputs, for each of the Qs, for each of the flip-flops. Then we put that design into Quartus for each of the D flip-flops. This was D2, flip-flop 2, flip-flop 1, and flip-flop 0. And then when we simulated it we can show that we got the proper sequence as the system progressed.